Howdy, howdy. This is Mr. Potter. What we're going to be talking about next in our PictureLab experiments is we're going to be talking about edge detection. So if I have some image, like an image of a swan, for example, and I want to know what the edges of a particular picture looks like, I'm probably going to want to compare pixels adjacent to each other. So let me go ahead and bring up a picture of a swan. I'm going to comment out this edge detection for right now and make sure that we're doing our edge detection program. So I just want to see what happens when we actually run this. And so I'm looking at a picture of a swan. The idea is that I'd want to be able to compare pixels at one particular point with pixels right next to it. And if I see a large difference between the pixel here and the pixel here, then that would constitute an edge. See how they go from all of these being in the hundreds to all of these being around 70. That would constitute an edge if I have a great disparity between the RGB values of one pixel and the RGB values of another pixel. So that's what we're going to be looking at here. So I've got this edge detection method. So I've got two pixels that I'm going to be dealing with, the left pixel and the right pixel. I'm going to be comparing the left pixel with the right pixel, and if they're different enough, and I'll talk about what different means in just a minute, then we say that this is part of an edge. And if it's not different enough, then we say it's not part of an edge. As we've done before, I'm going to get a matrix of pixels using the getPixels2D method for the picture. And I'm going to be keeping track of the color at a particular pixel. Now I want to go through every row of my image, but I only want to go through the up to the very last column -1. And I want to stop one short because if I'm going to have a left pixel and I want to compare it to a right pixel, the right pixel actually needs to be one more over. And so I actually need to stop short so that when I do column +1, I'm still within the range. Otherwise, I'll end up with that index out of bounds exception that we've dealt with before. So I get the color from my right pixel, and I need to compare it with my left pixel using this color distance method. Now what I'm going to do is I'm going to open up the pixel. I'm going to open up pixel file real quick. So if I go to pixel and I search for color distance, this is the color distance method. What we're doing is we have a red distance, which is my distance minus the test colors, red, the difference in green, the difference in blue, and then what I'm doing is the square root of red squared plus green squared plus blue squared, kind of a Pythagorean difference here. I'm doing red squared plus green squared plus blue squared, and then taking the square root. So this is a three-dimensional distance here. And as long as this distance is less than some threshold, this edge distance is going to be given to us as a parameter. As long as this color distance is less than that, then I'm going to color it black. I mean, as long as we're more than that much color away, I'm going to color it black. Otherwise, I'm going to color it white. So in other words, black is going to indicate an edge for us. White is going to indicate no edge. So I'm going to go back to my picture tester. I'm going to go back up to my edge detection method, and I'm going to uncomment this swan edge detection. And I'm going to go ahead and throw in a swan dot explorer before that, just because I actually do want to get two different pictures out of this. One of my original swan and one of my edge detection. And you can kind of see what's happening here. So here's my original swan, and here's the edge detection swan. And one of the things that you'll notice just looking at this is you see a lot of vertical lines. You don't see that many horizontal lines. And remember what we're doing is we're taking a pixel at one particular location and comparing it to the pixel immediately to the right. So here I've got 109, 105, 94. All of these values are close to 100. If I go one pixel over, now everything here is close to 40 something. And so that constitutes an edge for us. Notice that I'm always comparing pixels laterally here, side to side. And so I'm only going to get a change in vertical aspects here, because I'm only comparing left to right. Notice down at the bottom, I should have some edges down here, but I'm never actually comparing a top part with the bottom part. And because I'm never comparing top to bottom, I'm not seeing these edges. I'm not going to see very many edges along the bottom parts of shapes, or even on the top parts of shapes. It's not a very nice edge, even though this should be a very clear demarcation between the top of the swan and the dark water. But I do see a lot of it even in the aspect of the neck. I can even see some of it along here, and that's because we're using an edge detection of 10. If I were to change this to 20, and we run it again, we're going to see fewer edges detected, but the edges are going to be much truer. The thing is, I'm going to have a lot of contrast between this. So I see much clearer edges, a much clearer defined part of my swan. But again, notice that I have this problem with the bottom of the swan being completely non-distinct. Even though there should be a very distinct edge between the white of the swan, even though it's in shadow, we're also looking at the shadow of the water. And I also have some issues with this with the top of the swan's head and the bottom of the swan's head. And so comparing pixels side to side really isn't enough. I also need to compare pixels top and bottom. So we're going to talk about how to do that in today's lesson. So I've got this left pixel and right pixel, but I could have just as easily done pixel top pixel gets null and pixel bottom pixel gets null. And then of course what I'm going to need is instead of having a right color to compare, I'm going to want to have a bottom color to compare. And if I'm going to compare top to bottom, again, I'm going to want to stop one row short. So I'm going to make sure this loop actually stops one short. And I'm going to go ahead and say that top pixel is going to be pixels at row and col. And of course, y'all are going to notice something right now. I'll talk about in just a moment. Bottom pixel is going to be equal to pixels sub row sub col. And the thing is, I want to increase the row by 1. And then instead of having just right color gets right pixel dot get color, I want to say something like bottom pixel or bottom color gets bottom pixel dot get color. And then I'm going to change this if statement. So instead of comparing the left pixel and the right color, I want to choose the top pixel. And I want to do top pixel dot color distance for bottom color to be greater than this. So this should allow us to compare the top and bottoms. So now if I run this exact same method, now I'm only comparing top pixels with bottom pixels. And you can see that I have much more clearly marked edges at the top and bottom of my swan. And again, at the top of the swan's head and the bottom of the swan's head. But you start noticing that I'm starting to miss the edges wherever I have a vertical distance. Whenever I would have a vertical edge, I don't have a vertical edge to my rock, which I did have before. And so what I really need is something that kind of combines the essence of these two things. Not only comparing top and bottom, but comparing left and right. And so we're going to talk about how to best do that. So I've got these 3 pixels. I've got a left pixel, right pixel, top pixel, and bottom pixel, but I really want a main pixel. And I'm going to compare the pixel to the right and the pixel to the bottom. So I'm going to go ahead and get rid of this line of code. So I've got my main pixel, my right pixel, and my bottom pixel. And then instead of having a right color and a bottom color, I could just have a color, main color gets null. And I still want to go through this row by row, column by column, but this time I want my main pixel to be equal to pixels at row and column. I have my right pixel and my bottom pixel, but I don't need to worry about left or top because they're really the same pixel. That was the thing that y'all noticed. And instead of dealing with right color and bottom color, I'm only going to deal with main color. So I'm going to say main color gets main pixel dot get color. And then what I want to do is I want my pixels to compare themselves to main colors. So I want to say if right pixel dot color distance with main color is greater than edge distance or and then I want to have bottom pixel do the same thing. Color distance for main color. I'm forgetting to capitalize color. That's going to be an issue. But I want to make sure that this color distance is greater than edge distance. And if that's true, if my right pixel or my bottom pixel are too far away from the main thing, that I want to set it to black. So let's compile this, make sure this works. And there's a semicolon missing on this row right here. So it's the same idea. I'm just kind of pulling double duty. Cannot find symbol. And that's right. I don't want to do left pixel. I want to do main pixel. going to be setting the main pixel to that. So now I'm doing double duty here. I'm comparing horizontally and I'm comparing vertically, and so this should get me some really good edges here. So let's go ahead and run this again. So I can see my swan, and now notice that I have clear edges around the swan all the way around, both horizontally and vertically. I don't have the vertical lines that happen when I compare left and right, and I don't have the horizontal lines that occurred whenever I was comparing top to bottom. I actually have some pretty clear edges. I can even see the edges in the water from where I've got the wave, where I've got the darker water at the crest of the wave, along with the grayer water all around. So this is a pretty good edge detection here. And of course, if I want to get more edges detected, I can decrease this edge detection number here. I could decrease it back down to 10. The problem with that, though, is that anytime the color distance is more than 10, which really means anytime that the pixels are more than 3 away in the RGB direction, then I'm going to end up with, an edge being drawn. And so I've got a lot more of those here, but it's a lot messier. I really don't see as many edges. I see more edges, but it's basically noise that I'm worried about here. And of course, so I'm going to go back to 20, which seemed to get me some pretty good edges. So let me go ahead and run that again. And this is where we were. We got some really good edges here. If I bump this up to 30, again, I'm going to have fewer marks, but the marks that I'm going to be are much more distinct in my original picture, because they're 30 pixels, 30 color units away. So notice that I lose a lot of the detail from the rocks. I lose a lot of the details from the waves, except where I have obvious crests on the waves. But I've got a very, very good demarcation of my swan here. And so the larger this number is, the fewer points I'm going to see here, but the points are going to be much more distinctly, I am an edge. And part of when you're doing picture processing is you're going to have to find that sweet spot number experimentally. There is no hard and fast 10 always works, 20 always works. It really does depend on your image, and it really does depend on what you're trying to find for this particular image. So once again, this is Mr. Potter. Thank you for watching. Have a great day.